Now that we're experts at finding derivatives, we're going to spend almost the remainder of the course looking at how to undo differentiation. How do you undo a derivative? We call that finding an antiderivative or finding an indefinite integral. So those are the words we use for that process of figuring out what function had a particular derivative. So for example, if somebody told you that the derivative of y was equal to 2x, you would think, well, y could be x squared, or since the derivative of any constant is 0, there's a whole family of functions that have that derivative. There's something that we need to work on, and that is the issue of, we definitely know that the derivative of x squared plus c and plus any constant would be 2x. But if we're going the other way, we're saying what functions have that derivative 2x? Is this all of them, or could there be some others? So maybe there's some function that we just haven't discovered yet whose derivative is also 2x. So the one question that we want to answer in this section is that the only, are those the only functions that do that? So are these the only possibilities? Well, that's a big question for us. That's what we want to answer in these videos. Now, before we do that, I just want to tell you that this does have some sort of importance. It has a lot of importance in physics. In physics, let's say you have some mass and you just let it go. So the only force acting on it is gravity. Now, it may have some air resistance, particularly if you attach maybe a parachute to that mass or something, but let's say that the air resistance is so small in comparison to the force of gravity that it doesn't matter in this case. So if we're dropping a cannonball or something that's kind of compact and doesn't have a lot of air resistance, that would be probably a good assumption. So now, so the only force that's acting on that is gravity. And we know that the heavier you are, the more gravity pulls on you. So the force due to gravity should be proportional to the mass. It should be the mass times some constant. That constant we usually call g. Now, if I set this up so that down is in the negative direction, then I would say the force is equal to minus mg. I know something else from Newton's second law. The force should also be equal to the mass times the acceleration of the object. So that idea is that if you have something and you want it to accelerate faster, you know that you're going to have to push on it harder. So the force should vary with the acceleration. The more acceleration you want, the more force is required. Also, if you want the same acceleration for an object, but one object is more massive, you know you're going to have to push harder on the more massive one. So the force should also vary directly with the mass, and that's how we get this idea that force is equal to ma. So in this particular case, we have just one force, gravity, which is downward, and we also know that the force is equal to mass times acceleration. So we get this equation. The mass times the acceleration is minus m times this constant g, or the acceleration is negative g, where g is this constant that determines how strong gravity is. So call this sometimes we call it, since it in this case it is the acceleration, we call it the acceleration due to gravity. And that's basically constant. We know that if you go a long ways, gravity actually fades. So this is just an approximation to say that the force is just some constant times the mass. The true law is a little bit more complicated. It involves the 1 over the square of the distance between the two objects. But if we're not moving too far away from the surface of the Earth, then we can just assume that over that motion, the acceleration due to gravity is constant. Okay, so now our question is, we know that there's a relationship between the position and the acceleration, because if s is the position as a function of time t, and we know if we find the derivative of position with respect to time, change in position, respect to time, that would be velocity, right? And if we find the change in velocity is speeding up or slowing down, we call that acceleration. Okay, so really what we have here is an equation that says the second derivative of position is minus g, because the acceleration, that's what we've been calling a. Okay, the velocity, that would be, sometimes we call that v. Okay, in position s. So we have what we call a differential equation. We have information about the derivative of position, and from that information about the derivative of position, we'd like to actually recover the function that describes my position at any point. So to do that, we're going to have to undo some derivatives. Let's get a fresh screen here. We know that the second derivative of position, or that's the derivative of velocity, is this constant negative g. So knowing what we know about derivatives, what would have a derivative that's negative, or that's some constant? Well, it would have to be that constant times t, right? Of course, we could throw in any other constant, because the derivative of that constant would be 0. So we have to have negative gt plus some constant. In fact, in this case, because we have some object that's falling, we can actually give a meaning to what that constant is. If I plug in 0 for the time, then it wipes this out, and all I get is c. But v is the velocity of the object, so the velocity at time 0 is what c actually means. So a better name for c might be v sub 0. That would remind me that c is actually a velocity by calling it v, and it's the velocity at time 0 by putting a 0 down here. Now usually we say v naught, since naught is another word for nothing. It's all for naught, it's all for nothing. So v naught here. Okay. So what we've done is we had the derivative of velocity, and now we've recovered the initial velocity. Okay. Now the derivative, velocity itself is actually the derivative of position. So that's the first derivative of s, our position function. So now, if we know the derivative of position, can we recover the original function? Well, knowing what we know about derivatives, the things that have derivatives that are like t would be things that involve a t squared. And the things that have derivatives that are constants would be things that are multiplied by the independent variable t. Now let's see, if we check that and take the derivative, does that give us the right thing? Well, if I take the derivative here, I get negative 2 gt. Oops. So what I should do is throw a 1/2 out in front. I can do that because if I take the derivative, constants come through the derivative. Now by having this 1/2 here, when you take the derivative of t squared, the 2 comes down and cancels the 1/2, and you're left with negative gt. This works out okay, because if you take the derivative of v naught t, you just get v naught. But then there could be some other constant in here. I guess I've already used c for a constant, maybe I'll use d for that constant. In fact, in this case, because we're talking about an object that's falling, we could actually give a physical meaning to d. If in this equation you plug in 0 for t, it wipes out the t squared term and the t term, and all that's left is d. But s is our position, which you could think of as our height above the ground, and this is saying that d is actually the position at time 0. So rather than call it d, I could give it a more descriptive name. I could call it s sub 0. The s to remind me that it's a position, and I'm using s for my position function, and the 0 to remind me it's the position at time 0. So we have here s of t is negative 1/2 g t squared plus v naught t plus s naught, the initial height. You may have even seen this before you took a calculus class. You might have seen this equation for the height of an object as a function of time if it's just free falling, right? So with no air resistance, then this is the equation that discovers the position. Notice we've done something pretty powerful here in that we started from knowing information about the derivative of my function s, and by finding antiderivatives, I was able to find out actually what must the function s look like. That's powerful because this function allows me to tell how high will this object be at any future time. So in that sense, I can predict the future if I just know what is the value of this constant g, how much initial velocity does the object have, and what's its initial height. Then I can predict its height at any future time. So I can predict the future in that sense. Pretty useful. Okay, so we definitely want to do that. Now there's one thing that kind of should be making us nervous, and it's right here. If I if I find a function whose derivative happens to be the function I have, is that the only possibility? Is there something that I might be missing? Is there some function yet to be discovered that also does that? In which case, maybe the answer, maybe there's multiple answers to this question. If there are multiple answers to that question, then I could be in real trouble because I don't really know that I'm answering